Let's do another example for the power part. Problem 106, chapter 3. In this problem, we have this elevator, and the mass of this elevator is 1000 kilogram. And we have a motor here which is pulling this elevator up with the constant velocity of 3 meters per second. So it is moving it up with this system of pulleys and a cable. And we know the efficiency of the motor is 0.8. The efficiency of the system altogether, motor and maybe we have some frictions here, altogether is 0.8. And the question is, what should be the power of the motor? So the input power of the motor, which means how much this motor is putting power to the system. Okay. Again, I would suggest to stop this video and think about this problem. This is a very interesting problem. It is quite simple, but it looks to be very confusing. So I would suggest to stop this video and think about this problem for 5 minutes, 10 minutes. And then after that, come back and look at the rest of the video. So the motor is putting some power to the system, which we call it P in. And some of this power goes to, for example, heat, maybe friction in the system, and etc. But 0.8 of it goes to the actual work. The actual work here, or the output power of the system, is the fact that the potential energy of this elevator is increasing, right? Because the height of it is increasing. So that's going to be the actual work that we would like to do. We don't want to spend any energy on friction, noise, heat, etc., right? So the output power is gonna be the actual work that we are doing on this elevator. So probably most of you are gonna think about the details of this pulley and system of pulley and cable, but we don't really need to do any of those. We don't need to calculate the force in the cable, but if you do it, that's fine. But altogether, this system of pulleys are gonna apply a force to the elevator altogether, which is gonna be equal to the weight of the elevator. So T is gonna be mg. This force is being applied through this motor, right? The motor is applying this force, is tolerating the weight of this elevator and pulling it up. So the actual work which is done with this force which comes from the motor on the elevator is going to be the force times the velocity, as simple as that. So it's going to be T times velocity based on the equation that we just learned. So it's going to be equal to mg times the velocity. This is the actual output power, the useful work that we are getting in this system. Okay. But because the efficiency of the system is not 100%, the motor need to put more power to the system, right? This is not exactly the power of the motor. It should be more. The relationship between the actual power in the motor, which we call it input power, and the actual useful power that we are getting with the, from the system, you can relate them to each other with efficiency equation. So E is equal to P out divided by P in. Efficiency of the system is given. We know the output power of the system, so we can find the input power, right? So the only thing we need to do here is plugging the numbers. P out divided by efficiency, which is going to be equal to 1000 kilogram times 9.81 mg times velocity, which is 3 divided by 0.8, which is the efficiency of the system. Okay, so if you do that, then the input power is going to be 36.8 kilowatts. The unit is going to be watt. By dividing it to 1000, you're going to find it in kilowatt.